Remember guys, our mission is to understand nuclear chemistry.
We're gonna have to go really deep, right?
At least 3 levels into that.
Well, let's go.
That's the electron cloud.
What's that?
I guess it could be one of 3 types of radioactive decay.
Could it be alpha decay?
If it was, it'd be like a helium nucleus. That's when 2 protons and 2 neutrons leave an unstable nucleus that has more than 83 protons.
What about beta decay?
I guess that would be if it was an electron or a positron, which is an electron with a positive 1 charge. That's when a nucleus has too many protons, so one decays into a neutron and a positron, or when a nucleus has too many neutrons, so one decays into a proton and an electron, which leaves the nucleus.
There's a map on the back of the Declaration of Independence.
Isn't there something called gamma decay?
Yeah, that's when a nucleus is in a high energy state and gains stability by emitting some of that energy as a gamma particle or a photon.
What was that?
Must be an electron. Sometimes nuclei capture electrons whenever there are too many protons relative to the number of neutrons.
I don't really get how the nucleus works.
We're going to have to go down another dream level to explain that.
This looks like the nucleus.
Yep. The nuclear reactions we were talking about before are important because when they happen, the masses on both sides of the reaction equations don't match up.
Where does the mass go?
Remember E equals mc squared, Einstein's equation? The lost mass is converted into energy. That's how nuclear reactors work. In a fission reactor, heavy nuclei are bombarded with neutrons, making them unstable. The nuclei split, releasing lighter elements and more neutrons. These in turn break apart more heavy nuclei, which results in a chain reaction. The mass that is lost by one nucleus is small, but the mass lost by all of the atoms in a chain reaction is converted to a huge amount of energy.
That seems complicated.
Here's an analogy. The ping pong balls in this video are like neutrons. The first one hits a mousetrap, representing a heavy nucleus, which releases energy and more ping pong balls, causing a massive chain reaction.
And what is fusion?
While fission is the splitting of atoms, fusion is when 2 lighter nuclei combine into a heavier one. When they combine, they have less mass than when separate, and therefore release energy. This normally only happens at high temperatures and under high pressures, like in the center of the sun.
We should have taken the blue pill.
Can unstable nuclei exist outside of fission and fusion?
Yeah, take for example the element carbon-14. Carbon usually only weighs 12 AMUs, so carbon-14 has 2 extra neutrons. It's unstable.
What happens to it?
It goes through beta decay to become nitrogen-14, a stable atom. Although carbon-14 is unstable, it takes a long time for large quantities to decay. After 5,730 years, half of it is gone. That length of time is called its half-life. All unstable atoms have a half-life, but it varies from microseconds to millions of years. Carbon-14 is useful for a process called carbon dating. By knowing how much carbon-14 an object should contain, and then measuring how much it actually contains, one can tell how old it is.
So we learned a lot about the protons and neutrons, but what actually are they?
Let's go to the nucleus and find out. These are the particles that make up a nucleus, protons and neutrons.
Wait, why does the nucleus stay together? Wouldn't the protons repel each other because they have the same charge?
Well, we thought for a long time that protons and neutrons were indivisible, but they're actually made up of smaller particles called quarks. There are 3 quarks in a proton and 3 in a neutron. The quarks are held together by the strong force.
This is strong force!
The strong force is also responsible for overcoming electromagnetic repulsion between protons and gluing the nucleus together. It's one of the fundamental forces.
What are these forces?
Everyone knows about gravity. It attracts matter to other matter. The electromagnetic force causes attraction and repulsion between charged particles. We've just discussed the strong force. The 4th force is called the weak interaction.
What's that?
It's the force we know the least about. We think that it's responsible for beta decay. One of the down quarks in a neutron decays into an up quark via the weak force, resulting in the release of a proton and an electron.
So what mediates these fundamental forces?
I'm glad you asked. Particles exert forces on each other by exchanging particles with integer spin known as bosons. The 4 gauge bosons are listed on the standard model of chemistry. The strong force between quarks within a proton or neutron is created by quarks exchanging gluons. The electromagnetic repulsion you are well aware of is carried by photons. The W plus and minus and Z bosons are responsible for the weak force, which scientists know very little about. I'll show you a diagram that graphically depicts electron repulsion. The one electron emits a virtual photon, causing it to recoil. The photon then transfers its momentum to the second electron, resulting in the repulsive force we know as electromagnetic repulsion.
Wait, what particle is responsible for gravity then?
Scientists believe a boson, referred to as the graviton, is responsible for exchanging this force, but there is no evidence to prove its existence.
These forces are a bit over my head. Back up to quarks for a second. You're trying to tell me that all protons, neutrons, and electrons are made up of quarks?
You're right about the protons and neutrons, but electrons are their own subatomic particle. Electrons are actually a flavor of lepton. Leptons are fermions with half-integer spin and are believed to be elementary particles. There are 6 of them: electron, mu, tau, and the neutrinos of each, which have no charge. There really isn't that much interesting about leptons, other than they vary a lot in mass and are impacted by the Pauli exclusion principle.
So is this really the smallest stuff, or are you going to tell me that there's something smaller?
Well, there's something called string theory. It is a theory that all elementary particles have different properties because they are one-dimensional strings oscillating with different frequencies. Bosonic string theory refers to the original theory that this is only applied to boson particles. However, superstring theory postulates that there are strings of bosons and fermions that interact.
Do you really believe that?
Well, I believe in a unification of those previous theories known as M-theory. I think that strings are really one-dimensional slices of a two-dimensional membrane vibrating in 11-dimensional space.
And it will be like a taco inside a taco within a Taco Bell that's inside a KFC within a mall that's inside your brain!